Again, I want to now introduce some of the people that you saw in the video that are going to talk to you about their project of mapping microconductivity in cell types using high-throughput electron microscopy. So representing the team will be Joanne Buchanan, Dan Bumbarger, Derek Britton, Wenjing Yang, and Nunu DaCosta as well. So please join me in welcoming them.
I'm Joanne Buchanan, and I would like to be starting off with our fabulous team who did this work and you saw in the movie. I'm going to start out by thanking so many people who helped us with this project, not just the members of our team that you'll hear talk today, but also many people throughout the Institute in different departments like finance, purchasing, engineering, project management, and many other groups, including groups at Harvard. So today I'll speak first, then you will hear Dan, followed by Derek, Wenjing, and Nuno, and also a special shout out to our fearless leader, Clay Reed, and our awesome project manager, Shelby Sakau. So I think you saw this slide earlier today, and at the Institute, we have a multi-pronged approach to studying wiring diagrams of the mouse cortex. And different groups take different approaches, and we are especially focused here in the EM connectomics on looking at a cubic millimeter of previously imaged mouse brain. And a cubic millimeter is important because even though it might be the size of a sesame seed, we need to be able to have a complete dendritic arbor in order to understand a representation, an accurate representation of a microcircuit. This is the experimental workflow as the samples arrive in our laboratory. It starts out, It starts out with the functional imaging that occurs at Baylor College of Medicine. And these are transgenic mice that have a calcium sensor genetically encoded into their brain. And the awake behaving animal is studied using two-photon microscopy. That animal is then sent to us at the Allen Institute, and we start here with the sample preparation. The animal is perfused, and the brain is removed and sliced into 1.2 millimeter slices. It's then further trimmed down to the region of interest in the V1 visual cortex. Then that sample is processed for electron microscopy and finally embedded into a hard resin block. And this little chunk of black tissue that you see here, that represents the region of interest and the piece of the brain and the cortex that we are interested in. The block is then handed over to the sectioning team, and using a very sharp diamond knife cut into serial thin sections. Those thin sections are then collected and put into the different TEMCAs and imaged with high speed, high throughput. Finally, the images, the EM images, are stitched in a line and co-registered with the physiological data before they are then sent off to Sebastian Sung's team at Princeton where the final segmentation and 3D reconstruction happens. So now the question is, how do we prepare our tissue for electron microscopy? And as I mentioned, this is not a normal-sized EM sample, but it's rather large, a millimeter cube, which in our world is ginormous. So we need to stain an otherwise transparent tissue with heavy metals. And you can think about the electron microscope a lot like this cartoon here. The candle is the electron beam, the bunny is our sample, and the shadow on the wall is actually our EM image. So in order to make the shadow, we need to infuse our sample with heavy metals. And our primarily heavy metal that we use is osmium tetroxide. And we really like it because not only does it fix the sample, but it is lipophilic and thus stains the membranes, which is critical for the autosegmentation. It's followed up with en-bloc staining of uranyl acetate and lead citrate, and the overall goal for this is to avoid section staining, which could cause a lot of problems with precipitation and other forms of contamination on our very delicate sections. So you might ask yourself, why electron microscopy? It has a reputation for being very hard, and there are many, many technical challenges. However, the answer lies in these pictures. This is a very low magnification electron micrograph where you can see the cell body, and these large structures here are actually the dendrites of the cell. But what's in between all here in this neuropil? If you zoom in at much higher magnifications, you begin to see the exquisite detail of the brain, including the very tiny axons that are smaller than half a micron, on the order of nanometers, and the beautiful synapses that are equally tiny. So because these represent the wires of the brain, only the electron microscope can give us the resolution we need to be able to see them and follow them through serial sections. So it's very important that our samples have very well-defined membranes that are smooth and unbroken, because any mistake there can lead to a mistake in the autosegmentation. We also need very high contrast so we can do rapid imaging and even stain penetration all the way through these extremely large samples. And finally, consistency from sample to sample. I will now hand it over to Dan, who will tell you about the sectioning phase.
Okay, so the tissue prep that Joanne was talking about is really the foundation upon which everything else we do is standing upon. And once we get that little brain slice embedded in epoxy resin, the next thing we have to do is we have to do the slicing. We have to cut that into pieces. And we have to slice it in order to trace every single neuron and find every single synapse in that volume. We have to cut them at 40 nanometers thin, which is almost inconceivably thin. For example, if you were to cut a human hair at 40 nanometers, it would take you about 2,500 slices. And to get through that millimeter volume, we have to cut 25,000 slices. And that's just unfathomably thin and unbelievably difficult task to do. This is how it has historically been done. So we use a diamond knife, which is about the sharpest knife that you can imagine. We cut the sections, they float off into water. What you're actually seeing are ribbons of, there's maybe 20 sections there. We've got a little copper substrate with a hole in it and a thin plastic film that you take an eyelash to kind of guide those sections onto that thin plastic film all by hand. That thing is only 3 millimeters across. You can imagine that this is incredibly tedious, and the very best people in the world can only get data sets of a couple of thousand sections without having significant loss of sections. And so that does not scale up to our needs. So we have a couple of ways of trying to automate this process that should be able to and will scale up to meet those needs. And the one that I'm showing you here is based on essentially the mechanism of a cassette player. So we've got a tape system. This is a reel-to-reel tape system. And we do the same thing where we take a diamond knife and cut the section, float it onto water, but we use a piece of plastic tape as kind of a conveyor belt, and this plastic tape has holes with support film on it in the same way that the traditional substrates had. And with that, we have a very simple process that we can automate and hopefully reliably collect tens of thousands of sections without loss. And there are some, next slide will show the process going on. So what you're seeing now is the tissue block, which is the moving thing with the brain coming down on the diamond knife. The much larger slice, so these slices are about 4 millimeters long by 1.5 millimeters wide, coming off, and then you'll see it be taken up by this conveyor belt. And on the left is what it looks like when it's on the tape. You can see that it's placed over the aperture, and we've got a little barcode on that tape that allows us to track it through the whole process through imaging. And so this scales obviously much better to larger volumes, and it gives us the additional advantage that we can, instead of placing one sample in a microscope at a time, we can place a tape with 5,000 samples in that microscope, which obviously helps with the imaging later on. But in order to accommodate this kind of tape, we have to make a lot of modifications to our microscope, and Derek is going to talk about that. Thanks.
Morning, everyone. My name's Derek Britton. I'm a systems engineer, part of the manufacturing and process engineering team here at the Institute. I want to talk to you guys today really briefly just about some of the design principles we needed to, much we needed to modify a traditional transmission electron microscope in order to keep up with the throughput that's required for imaging a cubic millimeter. Let's see, this works? There we go. So last year we did a pilot data set for the IRPA Microns project, and we successfully imaged a small volume of roughly 250,000 images, giving us about 100 neurons. But we have to scale up to a cubic millimeter, which is considerably larger. So in order to accomplish this, we'd also have to, there you go. We also have to modify the electron microscope in order to keep up with the throughput rates. We're trying to get 250 million images recorded within a 6-month time period, which equates to, in terms of raw data, around 3 petabytes. Mind you, with the new modifications of our microscope, we could image this original data set here in about 3 days. Traditionally, last year took about a month. And then here is an example slide of a 1x1 millimeter montage, and here's actually one of the tiles of that montage at full resolution. Well, downsampled a little bit. So what are the requirements to actually modify an electron microscope to keep up with the required data rates? First, we need to have the microscope image by itself for a long period of time. Not many electron microscopes out there you can buy off the shelf can do that. Second, it needs to handle errors robustly and self-correcting any non-critical errors to basically maximize your uptime. Thirdly, we need to have real-time data quality control. We're talking about 3 petabytes of raw data that we have to sift through, and I don't think anyone wants to sit by hand looking through that stuff. So the machine has to make a go, no-go decision on every image that's recorded in real time. And in addition to that, we also have to be able to go back to any problem areas or target ROI regions to re-image if we do find other errors or problems in our data set. And then finally, we also have to maintain health of the environment of the microscope by monitoring the temperature, environmental conditions, as well as internal states of the machine to maximize uptime. And so we leverage here's just a few examples. There's many, many other things we've done, but here's some few highlight examples of things we've added to our transmission electron microscope that you saw in the video that was previously shown. First, we leverage a custom sample holding reel-to-reel system that we take the tape that Dan sections onto and we directly put it into the microscope. And in addition to that, we have leveraging a very large CMOS sensor, and we have a custom-built real-time GPU processing pipeline, which allows us to do a lot of the error handling and real-time image quality control abilities. And then to give you kind of a cartoon schematic before we hand off this part of the talk to talk about the actual imaging itself in terms of the pipeline and process, I wanted to show you exactly how we put these things together. So first, we install the reel-to-reel system, and then second, we add a column extension here, which increases our effective field of view without having to go to a high magnification. So basically, it's like an image projector. and it projects onto our scintillator down here, which converts our electrons into photons, which is then finally recorded by our camera array, or in this case, a large CMOS sensor. But now we will turn to Wenjing, and she'll talk about actually how we're going to accomplish this imaging task.
Hello, my name is Wenjing, and in this EM Connect Comics project, I'm mainly working on imaging. Before coming to this neuroscience work, I used to work for semiconductor industry for years. And there, I used electron microscope to look at transistors, the metal interconnects, and the circuits inside our computer chips. So now it's such a different and amazing experience to use the same tool set, but look at the fine features and the wiring diagrams inside our brain. As you've just learned from Derek's talk, with so many new features being added to a traditional transmission electron microscope, our goal is to develop an automated imaging pipeline that can handle this 1 cubic millimeter block. So we're going to divide 25,000 sections onto 5 scopes for parallel imaging. And each scope gets loaded with 5,000 sections on the tape. The tape is spooled onto a reel, and we feed the reel-to-reel system, going to feed the tape into the column of the microscope. Then each tissue section on the aperture will get imaged inside scope. Then the tape keeps going and being collected on the other side of the scope. And we expect to complete this whole imaging process in 6 months. To achieve that, we also want to ensure no section loss or damage. As you can see here, this is an example of an optical image with a tissue section on it. And each tissue section has a unique barcode, just like its ID. So we can randomly access these tissue sections later for any re-imaging purpose. And to complete the project, we also need uptime of all 5 scopes to be more than 60% of the time, and to achieve a pipeline imaging rate of more than 200 megapixels per second. And on the right is an example of 2D 1 square millimeter montage. From top down is pure to white matter. And this 2D montage combines about 10,000 tiles. If you zoom in on each tile, it's a high resolution EM image. And you can see how many details can be reviewed here. There's synapse, the vesicles, and membrane structures. And to collect each of this high-resolution tile, there are lots of work behind the scene. And basically, the tape is fixed down to a stage, and we rely on the stage move to access all the areas we want to image. And for each tile, the total cycle time is about 300 milliseconds, and this involves the stage move, settling, image capture where the camera shutter opens and grabs the image, and the quality control and the post-processing. For each day, our goal on one scope is to collect at least 40 sections and a total data rate of 5 terabytes per day. So if you're not an EM person, to give you a brief idea, this data size is previously about the amount of a PhD student's thesis work. So now we are able to get it on one scope just in 1 day. So during production mode, we will have 5 scopes running in parallel, and the total cycle time is going to be 250 megapixels per second, and a total collection of 200 sections per day. So here is a video recording of a real-time PyTemca, our imaging pipeline running. And as you can see, it steps through all these areas on the tissue, and the imaging rate is more than 3 frames per second. And if our network is working, I'll bring you to a website. So what you're seeing here is a real-time imaging. The scopes are collecting data right across the hallway from this room. OK, with that, I'll hand off to Nuno to talk more about interesting data.
So the next step, which we're not going to talk about, is to align and stitch and align all these sections into a coherent volume. And that's an effort that is being done not only by the Connectomics team, but in consultation with the array tomography team, the technology team, and our collaborators in Genelia Farm. What I'm going to talk mostly about is a data set that we collected last year that Derek already mentioned. Oh. Let me bring back the... our presentation. And what I'm going to start by showing is one of these simple black and white images of the cortex of the data set. And they are simple, they are black and white, and you, at this magnification, you can see somas and blood vessels and start seeing the dendrites. And as you dig deeper and deeper and go to IMAG, you start seeing that they are not that simple at all. You start to see, we start to see the fine little axons, and as you zoom in, you'll be able to start seeing the synapses like the one here, which is what we are interested in, because that allows us to identify where each neuron talks with another. So it is a black and white image, but the thing that Sebastian Sung did for us is color it using basically neural networks. And by coloring it, we could extract all the neurons that were on that volume, which was about 200 microns by 150 microns by 150 microns in depth, of which 40 microns were completely segmented. And from that, we could extract the excitatory neurons, of which we see here an example that matches nicely to one of the clusters of excitatory neurons that you see in IVSCC. The inhibitory neurons, and there's in this case there were 10 of them, and some of them we could also cell type. There's a Chandelier cell, there's a Martinotti cell, there's some basket cells. There's also 14 complete astrocytes and 5 microglia. And one interesting thing is that this segmentation, which was completely done automatically, could already, and will have some mistakes, which I'll show later on, could already get up to 1 millimeter of passing of axon, which is really, really impressive. As Clay mentions in the movie, most of the stuff that we are able to extract and visualize on this data set will take months before to reconstruct those neurons. So as I mentioned in the beginning, we have also the 2-photon image of these neurons. And this is a 2-photon data set collected by Andreas Tulias. In this case, he recorded the activity of a few hundreds of neurons. And you can see here now the data set completely registered with our EM, which allows us to see, which allows us then to map the connectivity diagram with activity of neurons. So this was a year ago. There was a few hundred. Friday last week, we just received our first candidate for the phase 2 mouse, where Andreas recorded the activity of about 75,000 neurons in vivo, and we now have this block in our hands to find the connectivity. And one thing that might have been missed before is why do we like a millimeter cube? It's such a nice number. And the reason is when you look at the morphology of neurons and you look how far their dendrite axons spread, and if you are in the center of that millimeter, and this diameter is roughly, for most cells, with the exception of maybe some layer 5 neurons, spreads about 500 microns. So if you are in the centers of that millimeter cube, we'll be able to get, in principle, the complete local connectivity of those neurons. So once Sebastian had reconstructed and we have combined the EM data set with the 2-photon, we can get a kind of a wiring diagram. And here's just to give you an idea of how much we progressed in the last year and a half. This is a paper by Clay that he started just before joining the Allen Institute. And this is basically the state of the art of published data in cortical functional connectomics. And there they they have interns and other people basically segmenting this data set. And it took them 23,000 hours to basically go through 3,400 synapses. And on the data set we collected last year, and this is proofreading of the segmented data set, it took about 39 hours to get to about 1,000 synapses. So it's about 100x, which is not bad. So I'm going to show you an example of the data now. And one thing that we are interested in this smaller data set before we get the larger one is the interaction between inhibition and excitation. And I'll show you an example from a cell, which is a Chandelier cell. You see here an example of their more complete harbor coming from our patch-seq pipeline. And like basket cells, this is the type of cell that controls the output of a neuron. And what's interesting about it, it's very specific, is that it has this, called Chandelier because it has these branches that are called candlesticks or cartridges. And in these cartridges, this cell innervates the initial part of the segment of axons. And here is one example from our data set, and here see now the axon targeting the initial part of a segment of a pyramidal cell. And again, yeah, look at this beautiful dendrite with all these spines reconstructed, again, fully automated. So I'll see if we can get to web browser. So this is the same data that I've shown you before, but you now must see that things light up. And that's because every single segment in this volume has been reconstructed. And now you see here some of the axons of the Chandelier cell. Oh, sorry. This actually shows how good the alignment is, because let me bring it back. The network is a bit slow. Okay, so here are two Chandelier cells. I know, because I've looked at this for a while, that one of the axons they are connecting to is this pyramidal neuron there from the border of layer 1 to 3 that should come out, which is now being generated. And you can see that you can basically bring to view every single neuron that is in this volume. And you can then, so one of the questions we are interested in is, do this, oh, it's still loading. Oh. Do these projections along this axon, do they cluster or they are equally distributed? Do the other cells that these inhibitory cells target, do they have similar receptor field properties, or they are just like the basket cells, just a sample of all different orientations of these similar receptive fields? And then again, you could go to every single axon and pick one, however you want. You can zoom in and visualize the structure of the, which is too slow here, but you are welcome to come to us and surf in our laptops. So one of the, before I finish, one of the approaches that we take here at the Allen Institute is this comparative approach, because if we are to, well, let me put this back. Wow, the network is really slow. So, because if we are to find general rules and principles of operation, if we are to find general rules of organization and operation, it's important to look over different species and over different areas. And some of the care that we took when developing this pipeline is to not make it dedicated for the mouse. And of course, one of the species that we are very interested in is our own. And I'm just going to show you now some similar video to the one I showed you in the mouse. But now it's from a human like ourselves, if the... Computer is really slow. I think the computer is frozen. Yeah. So what you'll see is basically a similar video, a similar black and white simple image, but now thanks to a patient that donated his brain, and thanks to the surgeons in a local hospital, and above all thanks to Julie Nihus, which managed to get the sample within 6 minutes from being a block of tissue sinking in a brain like our own to being in a fixative. And due to this very fast, we are, if the computer gets reanimated, you'll be able to see that the quality that we get in these human samples are very similar to the one that we're getting in the mouse, which makes us very excited about the possibility of being able to reconstruct it and segment it in an automated way in a very similar way that we're successful in the mouse. So, and you might not be able to run. So. Well, maybe we should leave it like that and answer questions, and then if the computer comes back, I can show you the movie.
So thank you to the team for the great talk, and if you have questions, please raise your hand so we know where to send the microphones. It's coming.
What is your game plan when you do the 1 millimeter cube where you have to stack up many smaller cubes to handle lateral connections? How are you going to stitch together the interconnections between the building blocks?
So in a way, the millimeter cube is to is enough to include what we think is it's one of those building blocks, and our thinking is more in going, instead of doing bigger volumes, is to go and find equal building blocks in different areas and different species. Having said that, Clay, which I think is around, has some ideas on how, through basically mapping the white matter out of this building block, to start connecting to other areas. But the idea really is, can we map this building block? Can we find their general rules of connectivity, and then go to a different area and see, are these rules still present? In which way do they vary? And so forth.
Hi, it's an extraordinary work. Thank you so much for making the talk. I have a question about your approach, if you were able to share some more of the details, how you approach the classification of the cells. So you have the neurons, various subtypes, the glia cells. It's a non-trivial task to safely, accurately split them all into the subtypes without actual genetic markers and so on and so forth. So that's, I'd like to learn more.
So for now, the only thing we can get is morphology, and from this however, so the things that we can get from other structures in the Allen Institute, like PatchSeq, is to get morphology and also the transcriptomics. So morphology, for now, serves to us as a link to these other modalities of cell type classification. Having said that, we have had quite decent success with using EM genetic markers like APEX. And so for some cell types of where this morphology is a dubious process, we might use those.
So there are quite a few places, for example, the mossy fiber granule cell synapse in the cerebellar cortex, where the structure of the glia seems to be very informative and important. Are you reconstructing glia around all of these synapses?
The glia is completely reconstructed. Our focus is really on the neuron part, but we hopefully the data will be shared to be available to people that are interested on glial aspects, astrocytes, and so forth. So
Sebastian's reconstruction.
Oh no, includes so on that slide with the different cell types, there are 14 beautifully astrocytes, which have these intricate structures that are very hard. And there are also 5 microglia cells. 3 of them are perinuclear, and 2 of them are perivascular. Yeah.
Thanks.
Okay. Well, is there one more question? Michael.
Gotcha. So in the 1 millimeter cubic reconstruction, what fraction of the excitatory and then of the inhibitory synapses will you have labeled with their neuronal activity, where you have the activity both of the target cell and of the source? Will it be a large fraction, or?
It'll be a considerable large fraction. So we got our first mouse. Out of the 100,000 neurons that we expect to be there, we have physiology from 75,000. So it will be a reasonable large fraction of them. Yeah, from the superficial layers to the deep layers, which are then imaged with 3 photon, while the superficial with 2 photon. Yeah.
And similarly of the inhibitory cells?
And yeah, so Andreas is using a paneuronal marker with the GCAM, so it's aiming at both inhibitory and excitatory cells. Yes.
Well, let's thank the EM Connectomics team again for a fantastic talk.